the presence of two CH2OH groups, two primary alcoholic group. And by these studies, as we did for glucose, they found that it will have a open chain structure like this: CH2OH, then CH, sorry, second carbon, it should be a ketonic group, so C double bond O. Third carbon is similar to that of glucose, OH on the left hand side, here in the right hand side, and the rest is same as that of glucose. The only difference is at the second carbon you will have a ketonic group. Okay, this is the open chain structure of fructose. Based, as we have discussed yesterday, they have studied the properties of this one, and they found that this is a six carbon compound, and it is six carbons are in straight line, presence of five OH groups, and they gives the characteristic reactions of the ketones. So based on that, they have found they have given a structure, open chain structure like this. Okay, and in as in the case of glucose, fructose also exists in a cyclic form. Okay, it also exists in a cyclic form, and the ring is formed between the ketonic group and the OH group of the fifth carbon. What will you say? What will you call the compound when a carbonyl group reacts with an alcoholic group? When a carbonyl group combines with alcohol, and when it forms a product having both OH group as well as alkoxy group on the same carbon, what will you call that compound as? What is the name of the compound? No idea.
Hemiacetal.
It is forming a hemiacetals. They are forming hemiacetals. Okay, and so here the hemiacetal formation is between the ketonic group, which is at the second carbon, and the OH group, which is at the fifth carbon. So hemiacetal formation is like this. As a result, you will get two forms, alpha and beta form. So this forms the first carbon, second carbon. This becomes the third carbon, and here COH and H, fourth carbon, OH and H. Fifth carbon is involved in the hemiacetal formation, and oxide linkage is formed between the second carbon and the fifth carbon, and last carbon is CH2OH. Now this forms the anomeric carbon. Second carbon forms the anomeric carbon, which is the asymmetric carbon, first asymmetric carbon. And here you can see that CH2 group, OH group is on the left hand side. So what will be this one? Alpha or beta? If CH2OH group is OH or CH2OH group is in the left hand position, we call it as beta. Okay, and you can see that here, if you look at this last asymmetric carbon, where will you find the presence of OH group? It is on the right hand side, so it should be D. It should be having D configuration, and it is minus, and we call it as fructose. What is minus represent?
Lever rotate.
So fructose is a lever rotatory
Liver
molecule.
rotate.
Fructose is lever rotatory, and it is D configuration because the OH group is on the right hand side on the last asymmetric carbon. So this is lever rotatory. So this is beta form. You can also have the alpha form, where the difference is that the configuration of the asymmetric, the anomeric carbon. Okay, so I'll write, if you are having CH2OH on the right hand side, it will form the alpha. it will form alpha. This is the first carbon, second, third carbon OH is on the left hand side. Okay, and fourth carbon, this is third, fourth OH is on the right hand side. Fifth carbon is involved in the ring formation with the second carbon hemiacetal form, and the sixth carbon is CH2OH. So how many atoms are involved in the ring formation? So we can call this one as beta. Sorry, this is alpha since CH2OH is on the right hand side. Alpha D minus fructose. Fructose. Okay. So how many atoms are involved in the ring formation? Are involved in the ring formation? Can you hear me?
Yes, sir.
But you are not able to see this picture. Can you see the picture?
Yes, sir.
Why you are not answering? How many atoms are involved in the ring formation? One, two, three, and four. Four carbon and one oxygen. So it forms a five-membered ring. Okay. So both alpha, this is beta, where so here and beta forms here we have seen. Okay. But one difference is here we should have this OH group, not this H group. The anomeric carbon it is OH.
Yes, sir.
Yeah, it is not hydrogen, it is OH. OH group will be present. Okay. So if it is the alpha form, and here we have OH group on the left hand side. So this is the beta form, not H, OH. Okay, beta form. Now here you can see that one, two, three, four, four carbon atom and one oxygen, five-membered ring is formed. Here also one, two, three, four, four carbon and one oxygen is involved in the ring formation. So a five-membered ring is formed in case of fructose, and this fructose ring structure of fructose can be represented by the Haworth representation. And in Haworth representation, it will have a five-membered ring which will have an analogy to furan. This is the compound furan, which will have four carbon atom, one oxygen atom in the ring. So it will have analogy similar to furan, and therefore we call it as a fructofuranose form. Fructose furanose form. Okay, furanose form, and this double bond will not be considered. Now it forms the this forms the first carbon. So you can see alpha forming uh, as we did in the yesterday. We are doing the same thing. So this forms the first carbon, second carbon, third carbon, fourth carbon, and fifth, sixth one. And you look at the second carbon, where CH2OH is on the left and OH is on the right. Whenever whatever groups are coming on the right hand side, where will you keep the groups? Whenever
Below, sir.
groups
Downside.
below. So you can see that CH2OH comes at the top, OH is below, the third carbon, OH is on the left, so it is at the top, then hydrogen is at the bottom, here OH is at the bottom, it, and last carbon, CH2OH only is present, so there is always, it should be fixed, as I told you, and C6H5, OH is at the top and H will be at the bottom. Are you getting this one? Are you getting?
Yes, sir.
Yeah.
Yes, sir.
Uh, or if you want, I will show this representation for your convenience. So we are first writing the uh, Furano's form. So this is the Furano's form. So this becomes the second carbon, third, fourth. This carbon will be fifth and sixth position. You will have the CH2OH as the sixth carbon. Now look at the second carbon. This is the second carbon where OH group is on the right, so it should be at the bottom, and the CH2OH is at the top. It is on the left, so it should be at the top. Third carbon OH is on the left, and hydrogen is on the right. Fourth carbon OH is on the right, hydrogen at the left. Fifth carbon, uh, uh, as I told you, the groups are fixed. One is CH2OH, which is at the top, and hydrogen will be at the bottom. Okay, so what will be this form? Alpha or beta? OH is at the bottom in the second carbon, so it will be at alpha or beta.
Alpha, sir.
It is alpha D, okay, minus fructo furanose. Since it is in the furanose form, we call it as fructofuranose. And if OH and CH2OH, if they interchange their positions, then it will become beta form. So that is the representation of fructose molecule. Okay, and that is all about the monosaccharides. And about disaccharides and polysaccharides, this year it is not there. So that is why we are not going to discuss about the disaccharides and polysaccharides. And normally in disaccharide or in a polysaccharide, two monomeric units, two monosaccharide units, they are linked together by an oxide linkage, which is formed by the elimination of one water molecule between the two OH groups. And this linkage between two monosaccharide units will be known by the name glycosidic linkage. So this is what glycosidic linkage. That is for a polysaccharides or a disaccharide. The two monosaccharides are linked by one oxide linkage between them, and this oxide linkage is formed by the elimination of water between OH groups of two monosaccharide units. So that is what we call as glycosidic linkage. So if you are somebody is asking you what is the linkage in a carbohydrate in a polysaccharide, what is the linkage? It is glycosidic
Glycosidic.
glycosidic linkage. Okay. So see here you can see that this oxide linkage is between two monosaccharide units is known as glycosidic linkage, and this is the actual representation glycosidic linkage in a sucrose molecule, and it is between first carbon of the glucose molecule, and it is between the second carbon of the fructose molecule. And since both the first carbon is aldehyde carbon, second carbon is ketonic carbon, since they are involved in the bond formation, it will be a non-reducing sugar. I told you we discussed about reducing and non-reducing sugars, and I told you whenever aldehyde or ketonic groups are free, it will be reducing, and whenever aldehydic or ketonic groups are involved in the bond formation, it will be a non-reducing. So here, first carbon is the aldehyde carbon, second of the glucose, and second carbon is the ketonic carbon of the fructose, and they are involved in the glycosidic linkage. So it will be a non-reducing sugar, which is a disaccharide sucrose. Okay. And when you're talking about maltose, maltose is made of two molecules. One is glucose unit, and the other one is uh, yeah, another one. It is two alpha glucose units are linked, and the second one is the alpha glucose unit. So this is what maltose is. Okay. And when you're talking about maltose, maltose is made of two molecules. One is glucose unit, and the other one is two alpha glucose units are linked, and the second one is and the glycosidic linkage is between first carbon and fourth carbon. Even though it is not there in the topic, just for your sake, and just touching up this thing. So maltose, it is a disaccharide. When it is maltose is hydrolyzed, you will get 2 alpha glucose units, and the glycosidic linkage will be between first carbon and fourth carbon of the glucose. First carbon of the first alpha D glucose, and fourth carbon of the second alpha D glucose. And here, even though here first carbon is linked, this carbon of the second glucose unit is free. So will it be reducing or non-reducing?
Reducing.
Reduce.
It is reduced because this carbon is free. The carbonyl or aldehyde carbon is free in the case of glucose, so that is why it will be reducing. So if you are talking about lactose, which is milk sugar, it is composed of glucose and galactose. Lactose is not glucose; it is between glucose and galactose, and you can see that this is the lactose. Galactose, which is which will different from glucose in the configuration of the fourth carbon. In the third and fourth carbon, you can have OH group on the left hand side, then it will be forming galactose. It is similar to glucose only. It will differ the configuration of the fourth carbon, where OH group is coming on the left hand side in galactose. And it is between first carbon of galactose and the fourth carbon of glucose, and hydrolysis of galactose will give you hydrolysis of lactose will give you galactose and glucose. Okay. Then starch is made of alpha glucose units, and it will have two components, amylose and amylose pectin. Amylose is water soluble. It is unbranched, and it contains 200,000 alpha glucose units, uh, and it will form the about 20% of the starch. The second unit is amylopectin, which is water insoluble component. It is branched, and glycosidic linkage is between the C1 and C4 for the straight chain, and the branches will be between C1 and C6 of the monomeric units, and it constitutes about 80%. So another one is cellulose. Cellulose is also made of glucose, and it is beta D glucose units, and here also C1 and C4 are linked together. Glycogen, carbohydrate is stored in the body as glycogen, and it is known as animal starch. Okay, and it will have a branch structure similar to amylopectin. Okay, that is all. So we are not much worried about. You should be learning for your the exam. You should be learning only this monosaccharides, glucose as well as fructose. Then we are moving on to amino acids. So amino acids, when we are talking chemically, they are the compounds that contain an amino group and a carboxyl group. Amino group and carboxyl group. And amino group uh, is basic, and carboxyl group is acidic. Okay, so that is why the name amino acid, and they form the basic units for the proteins. Proteins are made of amino acid. It's a polymer of amino acids. Proteins are nothing but polymer of amino acids. And all naturally occurring amino acids will have uh, uh, will be alpha type. So amino acids can be different types. Generally, it can be alpha amino acid, it can be beta amino acid, or it can be gamma amino acid, depending upon the relative positions. So if I talk like this, take like this, NH2, CH2, COOH, NH2, CH2, COOH. So if you look at the relative position of NH2 with respect to COH, what is the position of this one? With respect to COH, what is the position? What is carbon? With respect to COH, this
Second
carbon is alpha carbon. So we call it as alpha amino acid. Okay. NH2, CH2, CH2, COH. With respect to this COH group, this is alpha, this is beta, so we call it as beta amino acids. Then if it is one more carbon is there, we will call it as gamma, delta, likewise it will go on. And all naturally occurring amino acids are alpha amino acids. All naturally occurring amino acids are alpha amino acids. That means the amino group, the relative positions of amino group as well as the carboxyl group will be at the alpha position. Relative positions will be alpha. So with respect to one, the other will be in the alpha position. Okay. And amino acids forms proteins. 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 And proteins are made of amino acids. And it is made of alpha amino acids. It is made of alpha amino acids. And proteins, if it is hydrolyzed, what will be the basic unit you are getting on the hydrolysis of protein?
Peptide.
Hydro, if it is when a saccharide is hydrolyzed, you will get a monosaccharide.
Amino
Similarly,
acids.
when a protein is hydrolyzed, you will get an alpha amino acid, which means that proteins are made of alpha amino acids. And the name itself, protein, it comes from a Greek word proteos, which means of prime importance. Proteins comes from proteos, which is of prime, which means that prime importance. Okay, and they form the structural elements, or it forms the structural elements. Proteins form the structural elements in the molecules, and it is very much required for the structure and functions of life, and they form the fundamental basis of life. Okay, and it is made of amino acid units. And proteins will carry out many functions. The enzymes which are in the body, they are nothing but proteins. What is the role of enzyme?
Catalyst.
They are
biocatalyst.
biocatalyst.
Access catalyst.
Yeah, hormones are nothing but proteins. What are hormone? What is the role of hormones? They regulate various body functions. The various body functions are regulated by hormones, so they are nothing but the proteins. Then antibodies, which the substances that protect our body against infections or external uh, toxic substances. So they are antibodies. Again, they are this one. Then uh, the muscle tissues, keratin, which is the present in the hair, and the muscle tissues. All these are made of proteins. Okay. So likewise, proteins plays a very vital role in the life. Okay, for the maintenance of life. So that is why we are discussing about these proteins. And as I told you, proteins are made of amino acids. Amino acids will have amino group as well as carbonyl group. With respect to relative positions, we will call it as alpha, beta, gamma, delta, etc. But all naturally occurring amino acids will be what? All naturally occurring amino
Alpha.
acids
Alpha amino acid.
will be of the form alpha form. And the amino acid can be generally represented by this formula RCHNH2COH. You can see here the relative position COH and NH2 group. They are in the alpha carbon, so it is this alpha, this one. And R group can be a complex group. It is a side chain and it can be will contain the side chain may contain some other functional group. It may contain amino group. The side chain may contain acid group. So that is why it's a complex group. And the simplest amine or amino acid is obtained when R group is hydrogen. Am I right? When R group is hydrogen, the simplest amino acid is obtained. So what is that amino acid?
alpha amino acid.
Alpha. What should be the chemical formula of that amino acid when R is CH? Sorry, R is hydrogen. It will become NH2 CH2COH. Am I right?
CH2CO.
NH2 CH2COH, and that is the simplest of all of alpha amino acids, and that is called as glycine. It is known as glycine. Okay, and when R group is CH3, when R group is CH3, that forms alanine. That forms alanine. So the two simple amino acids, at least you will learn. One is the first one, what I wrote. This is what we call as glycine. Second one is CH3 CH NH2 COH. This is what we call as alanine. Alanine. And here, what about this glycine? Will it be optically active?
No, sir.
No. Why?
No,
There is
sir.
no asymmetric carbon.
No hydrogen.
Two hydrogen to the same carbon. Okay. Now, what about this one, alanine? Is it optically active?
Yes, sir.
Yes,
It will
sir.
be yeah, it will be optically active because this carbon is asymmetric carbon and it is attached with four different groups. And generally, I can say it can be represented as CH, COH, NH2. Here you will have R. R can be any complex group as well as simple groups like hydrogen and CH3. Okay. And when you see when the R group is isopropyl group, it will be called by the name valine, VALINE. Likewise, we will have different compounds. Okay. Uh, all will be alpha amino acids. And except glycine, all other naturally occurring amino acids will be optically active. So all except the glycine, all other amino acids will be optically active. They will show optical activity. And you have 20 naturally occurring alpha amino acids. We have 20 naturally occurring alpha amino acids. And when you are naming these names of the amino acids, will normally they will be represented by their trivial names. They will have a common name, and normally this name is related with the property of the compound, property of the amino acid. You can see glycine is what is the what should be the actual name of glycine? IUPAC's name. If I give what is should be the name of glycine? IUPAC's name of glycine NH2 CH2 COH. What should be IUPAC's name? 1 2. Tell me. 2 amino
2 amino
ethanoic
acid.
ethanoic acid. Okay, 2 amino ethanoic acid is the IUPAC's name, and it is a trivial name. And this glycine name derived from derived due to its taste. It is sweet in taste. Glycose, which means sweet in taste. So that is why. So you can, if you are talking about the another one, triosine. triosine, another amino acid, and which will have the name because of which is it because it is obtained from cheese. So that is why triosine. And all amino acids, when you are talking about the trivial names, they end in ine. Yeah, ending word will be ine. Okay. And normally these amino acids, when you are representing, they will be represented by a three-letter word or a one-letter word. So if I am talking about glycine, we can represent as GLY. GLY stands for glycine, or we will also use G, which stands for glycine. And when you are talking about this alanine, alanine can be represented as ALA or capital A. So as I told you, they will be represented by a three-letter word, or they can be abbreviated with a three-letter word or a one-letter word. Okay. And similarly, valine, it will be VAL or V. And how many such alpha amino acids are there?
20.
20.
There are 20 such
20.
alpha, 20 such alpha amino acids. And all amino acids will have L configuration. All amino acids will have L configuration. And they are assigned L configuration with respect to this compound. Here, if the NH2 group is on the right hand side, then we call it, they will say that it will have the D configuration. And if NH2 group is on the left hand side, it will have L configuration. That is how we are giving L and D configuration. And as I told you, all naturally occurring alpha amino acids will have NH2 group in which side?
Right side.
L. I told you all amino acids are L will be having L configuration. So where will you have the
And
NH2 group? This is L. It should be on the left hand side. NH2 group should be always on the left hand side for alpha amino acids which are naturally occurring. Okay. And on the basis of their requirement in the body, amino acids can be classified into two categories: essential as well as non-essential amino acids. Essential and non-essential amino acids. Amino acids which can be synthesized in the body are non-essential, which can be prepared in the body. They will be known by the name essential amino acids like glycine, alanine, etc. And essential amino acids are there are which cannot be synthesized in the body, and it has to be supplied through diet. It has to be supplied through food. Such amino acids are they are essential. Otherwise, it is non-essential. And if you are talking about valine, leucine, all these are essential amino acids. If we are taking these 20 amino acids, 10 will be essential and 10 will be non-essential. Out of the 20 naturally occurring amino acids, 10 are essential and 10 are non-essential. And all these amino acids will have L configuration. Okay. Now, another way of classifying these amino acids is on the basis of the relative number of amino group as well as COH group. They will be classified as neutral. They will be classified as acidic amino acid, and they will be called as basic. This is based on the number of NH2 and COH groups. Based on the number of NH2 and COH. What is the nature of NH2 group? What is the nature of NH2 group?
Basic.
It is basic and COH
Basic.
is acidic. And if you have the same number of acidic and basic groups, what should be the nature of that amino acid?
Neutral.
same neutral. So if you have same number, if you have equal number of NH2 or CH group, as in the case of glycine or alanine, they will be neutral because they have same number of NH2 and CH group. And if the number of COH groups are more than NH2 groups in an amino acid, then it will be acidic. And if you have more number of NH2 groups than COH groups, so it can be basic. From where this NH2 and COH will come? So tell you like this. We have seen that they have the general formula R CH2 CH NH2 COH. Okay, R group can be anything, and it can have a complex group structure. Let me say, if the R group in this molecule is uh, HC HOOC CH2, then again you CH2 COH and NH2. So R group is this group, CH2 COH group, and this is known as aspartic acid. It is an amino acid. It is known as aspartic acid. Will it be acidic or basic?
Acidic.
It is acidic because it has
Acidic.
more number of this one, more number of acid groups. Now another amino acids where uh, we have this group NH2 CH2 4 times as the R group. Then you have the other groups like here H, COH, and NH2. So the name of this acid is lysine, Lysine, lysine. It's an amino acid. Amino group and acidic group are there. But which is more in number, amino group or acidic group?
Amino group.
Amino group. So what should be the nature of this amino acid?
Basic.
Basic.
Basic. So that is what I told you. Depending upon the relative number of acid groups and basic groups, you can classify them as acidic, basic, or neutral. If the number of the functional groups are same, then it will be neutral. If you have more acids, it will be acidic, and if you have more amino group, it will be basic. Okay, and these amino acids are colorless. Normally, they are colorless crystalline solids, and they will be soluble in water, and they will normally have high melting and boiling points, and they will be normally existing in the salt formation instead of acid or a base. They will be normally existing as an acid. Sorry, they will be normally existing as in the form of a salt, and that is what we call as they exist in sitter ion form. Sitter ion form. What happens is that you have an amino acid with the COH group, which is acidic, and NH2 group, which is basic. And in aqueous solution, what happens is that this acid will donate its proton, and the base will receive the proton, and it will become a R CH CO minus and NH3 plus, like this. And this internal dipolar ion, which have both cationic part as well as anionic part within the molecule, that is what we call as a sitter ion. Amino acids behave as salt rather than simple amines or carboxylic acids, and it is due to the presence of both acidic and basic group. In aqueous solution, the carboxyl group will lose the proton and the amino group will accept the proton, giving rise to a dipolar ion, which has a cation as well as anion within the molecule, which is known by the name suitor ion. And this suitor ion will be neutral, but it contains positive and negative charges. Are you getting? Are you getting or not?
Yes, sir.
It's very important. It is very important. Amino acids are existing as positive charge. Suitor ions. So here you have R group, CH, COOH, NH2. Acidic group will donate its proton to the basic group, and as a result, it will be existing in this form R, CH, COO minus, and NH3. So it is a salt because acidic and basic groups are present, and cations and anionic group are present within the molecule. And we call it as a dipolar ion. Two poles are there, positive and negative poles are there. It is known by the name Switter ion. Switter ion. How will you get a Switter ion? Due to the formation of an internal salt. When the same molecule contains acidic and basic groups, they will form a dipolar ion, which is known as Switter ion. And this Switter ion will be amphoteric in nature. Switter ions will be amphoteric in nature. They will both react with the acid as well as a base. Amino acids show amphoteric behavior because NH3 group, they can donate a proton, and or COH group, CO minus group, they can accept a proton from an acid, and NH3 group, NH3 plus group, that can donate a proton, so they will react with both acids and bases, so it shows amphoteric behavior. So Switter ion will be amphoteric in nature. So the remaining things regarding the structure of the proteins and amino proteins we will discuss in the next class. Okay. Any doubts?
No.
Any doubts?